Alright, so in this particular video we are going to look at how to interpret change in exponential models by changing a particular unit known as time. So what we're going to do is take a look at some things, write some things down, see if it will be useful in how to solve these problems. It says after a certain medicine is ingested, its concentration in the bloodstream changes over time. The relationship between the elapsed time t in minutes, I'm going to put t is equal to minutes. Since the medicine was ingested and its concentration in the bloodstream, C of t, in milligrams per liter is modeled by this function. All right, so here's our initial value. All right, I'm going to call that A. This is our decay factor, B, and this is over time in minutes. All right. So complete the following sentence about the hourly rate of change in the medicine concentration. Every hour, the medicine concentration decays by a factor of what? And so we need to round our answer to 2 decimal places. So right now, this is the decay factor, all right? It's a decay factor per minute, all right, per 1 minute. So basically think of it this way. In 1 minute, it keeps 96%, all right, of whatever it has, and it loses 4%. So right now, every single minute it loses, ready? It loses 4%. So how much would it lose over an hour? So think about it this way. If it loses 0.96 per minute, per 1 minute, how much would it lose in, say, 60 minutes? All right? Because there's 60 minutes in an hour. So I'm going to type that in, right? So 0.96. You could use parentheses, obviously, to the power of 60, which is the same as 0.96 in parentheses to the power of 60. All right. So to 2 decimal places over an hour time. Wow. So here we go. There's 2 decimal places, so I got to round that guy. So I'm going to put 0.09. All right. So right here, 0.09. There you go. So let's go back real quick, see how I did that. Real quick. So this one, it said this was the decay factor per minute, but we had to change it to an hourly rate. So that's why we raised it to the power of 60, because there's our 60 minutes in an hour. And that's it. All right, let's go to the next one. All right, I'll take a little screenshot of this. We'll write some things down. All right, so it says Fred started studying how the number of branches on his tree grows over time. So the relationship between the elapsed time t in years, so put t equals years. There we go. And the number of its branches, b of t, is modeled by the following function. So it looks like we started with 20 branches, and then it's growing at a rate of 2.5. So basically 250% per every single year. Complete the following sentence about not the yearly rate, but the monthly rate. All right, so what does 2.5 represent? 2.5 represents the yearly rate. So in 1 year, we're going to take 20 and multiply it by 2.5, and that will give you its yearly rate. That would be the yearly factor or growth factor. We got to change it from yearly to monthly. Well, there are 12 months in a year, so I think the monthly rate, can't just put a 1, I got to put a 1 over a 12, because 1 out of 12 is considered to be a month because there's 12 months in a year. So let's try that. So we're going to do parentheses 2.5, and we're going to raise that to the power of 1/12, okay, because there's 12 months in a year. Get 1.08 if I round that, right? 1.08. So it says round to 2 decimal places. So put 1.08 right there. All right. Make sure I got it right. Yeah, got to round it up. 1.08. See if I got it. Woohoo! 2 for 2. Looks like we're doing this the right way, huh? All right. Laurent invested some money in a bank account. The relationship between the elapsed time t in decades. So here's what I always start with. I always kind of write down what my time is. So in this particular case, t is equal to decades. Not d8, sorry. Decades. Since Laurent invested the money, the total amount of money in the account, so m of t is the total, looks like she started out with 4,900, and it's multiplied by 1.5, so it basically gains 50% in a decade. All right. So we got to figure out, here's the decade part. All right, so here we go. I'm just going to write down my decade rate. All right, 1.5. Now, if I raise that to the power of 1, that's like in one decade. Now, what is a decade? It's a total of what, 10 years, right? A decade is equal to 10 years. So if we want to go from a decade to just not a decade rate, but a yearly rate, we got to take that decade and we got to divide it by 10, and that gives us our yearly rate. And that'll tell us what we increases by what factor. All right, so if we want to go from decades to years, that means we got to do 1/10. But if we want to go from years to decades, then we have to raise it to the power of 10, conversely. All right, so let's go ahead and do 1.5. All right, and we will raise it to the power of 1/10. So every single year, it's going to go up by 1.04. Basically, it gains 4% every single year. So I'm going to put 1.04 right there. See if it works. 1.04. Woohoo! Man, we're on a roll here. All right, last ones. All right. It says after the last ice age. All right. Began, the number of animal species in Australia changed rapidly. All right. The relationship between the elapsed time t and years. So once again, I'm going to put t equals years. It's always a good reminder when I'm doing these problems, like, all right, t is years. Since the ice age began, the total number of animal species, S of t, is modeled by the following function. Well, we start off with 25 million, and it's decreasing. Looks like it's decreasing by a 22% rate, so it's keeping 78%. All right, so this is the yearly rate. Oh, but now we need to go from yearly to a decade. So what is this 0.78? 0.78, if I do it to the power of 1, that's per year. But if I want to do it per decade, I got to raise that not to the power of 1, I got to raise that to the power of 10, because there are 10 years in a decade. So that's why I got to put that 10 right there. So now I'm going to go over to my calculator. Type in parentheses. There's my decay factor per year, but we got to raise it to the power of 10 because now we're going from years to decades. So every decade, whew, wow, look at that decay factor right there, 0.08. That's what I'm going to write right there, 0.08. Put 0.08. And that's it. All right. So if you mess up, you can see a step-by-step solution. Okay, they do the same thing, basically the same thing. They talk to you about it. They talk about years and how there are 10 years in a decade, so that's why they raised it to the power of 10, and that's how they get that 0.08, that's the approximate value. That's all you got to do. So good luck with that, and I hope this was helpful when you were working on these problems dealing with changing units of time in an exponential model. Have a great day.